Hello, my name is Andrew Geary, and welcome to Seismic Sound Off, in-depth conversations in applied geophysics. In this episode, we highlight Sid Misra's course on machine learning techniques for engineering and characterization. Sid provides a great background on machine learning and the value it brings to geophysics, why the coding language Python is essential and easy to learn, one action you can take today to succeed in the field, and the advantages of virtual courses over in-person events. If you want to understand machine learning better and its impact on geophysics, listen to this episode. While Sid's tour is currently canceled due to COVID-19 coronavirus concerns, Sid and SEG are actively working on a virtual course to take its place. Visit seg.org/education for the latest information. Dr. Misra is an associate professor in the Harold Vance Department of Petroleum Engineering at Texas A&M University. Recently, he was awarded the prestigious Department of Energy Early Career Award, American Chemical Society New Investigator Award, and SPE Mid-Continent Formation Evaluation Award. His research interests include subsurface characterization, machine learning, sensing and sensors, and inverse problems. Now, enjoy our conversation. So, please, could you provide a brief overview of your machine learning techniques for engineering and characterization course?
Okay, Andrew. So what I'll do before I kind of provide you the brief overview, I just want to make one thing clear for my audience and people who are interested. I want to differentiate between AI, machine learning, and deep learning, because if we understand this difference, then we can understand the outline for this course a bit better. So what I mean by artificial intelligence is a branch of computer science focused on developing algorithms inspired by certain aspects of natural intelligence. And the goal of these AI methods is to perform tasks requiring human intelligence. One example would be visual perception, speech recognition, and reasoning. Now, in engineering, in geophysics, in geoscience, we are not using AI at this point of time. What we are using instead is machine learning. So what is machine learning? Machine learning is a subset of methods that will help us achieve AI in the long run. This course is for machine learning, and it's completely focused on machine learning. So what is machine learning? These are a bunch of algorithms that can work on large data sets, and these large data sets are also referred as big data. Machine learning algorithms, they build data-driven models based on the input data that you provide. And the goal here would be to develop data-driven models that can help a geophysicist, a geoscientist to make predictions, to generate some recommendations. It will help make decisions and so on. Okay, so that's machine learning. And now the third thing, which a lot of people get confused, is deep learning. Deep learning is a subset of machine learning. So AI contains machine learning, and deep learning is inside machine learning. So it's a subset of machine learning. And what deep learning is, these are the new methods. These methods have evolved over the last 10 years. And the reason they are new is because they depend a lot on very large data sets. Machine learning algorithms can work with a data set, let's say, which is 100 MB or let's say 1 GB. But for deep learning, you need bigger data sets, 10 GB, 15 GB, 1 TB. So these are latest algorithms that require a lot of data. Now, if an algorithm needs so much of data, it means it needs a lot of computation power. So that's why NVIDIA and companies like Google, they are developing GPUs, TPUs. These are not CPUs anymore. These are highly advanced processing units that process these big data sets. And when you create these machine learning algorithms for such big data sets, these are called deep learning methods, right? So now that you understand the difference between AI, ML, and DL, I'll try to mention what is the objective of this course. Now, this course is designed for machine learning. And inside machine learning, there is deep learning. So this course will discuss deep learning, but in this 2-day course, I think only 15% of the course is dedicated to deep learning. 15, right? So this course is designed for engineers, researchers, geoscientists, and it will help them learn to assemble machine learning workflows. It will help them to apply machine learning on various types of data set. Day one involves setting up your computer, your laptop for performing machine learning operations. So let's say 1 hour of day one starts with setting up your computer and downloading all the data that you will need for this course. Now, once we are done with the setup, it generally takes 1 hour, not more than that. Once we are done with the setup, we move into supervised learning. Supervised learning is, again, a way in which you can perform machine learning. Supervised learning needs data, it needs a target. One example of supervised learning is classification methods. So we'll talk about classification methods. I'll show you how classification methods can be used to detect outliers. I will show you how classification methods can be used to perform rock typing. So this rock typing is a case study where you'll work on some real data and you'll perform a rock typing. You'll solve a rock typing problem. So we'll start off with classification and then we'll move to regression, which is also a supervised learning technique. For regression, I'll provide you a case study, which is prediction of water saturation in the subsurface. Now, as a lot of geophysicists and geoscientists, you're working on solving hydrocarbon saturation problem in the subsurface, this particular case study will help you understand how a machine learning can be used for predicting a continuous depth-based water saturation in the subsurface. And this day one will end up with a case study where we'll apply machine learning methods on an image. An image is a 2D distribution of data. When you work on seismic map, it's also a 2D or a 3D distribution of data. So this particular case study, it's a very basic case study which will help you extend these machine learning algorithms to seismic maps, which might be bigger, but all the concepts that you learn will be the foundation of working with images, which is a 2D distribution of data. In this case study, we'll talk about feature extraction as well. And a machine learning algorithm depends a lot on how good of a feature extraction you can perform. So here I'll show you different ways in which you can use open source methods for feature extraction. So that's day one. And day two is focused more on creating robust, reliable, data-driven models using machine learning. Now, day one is all about developing machine learning methods, but day two is about ensuring how you ensure that these methods that you have developed, these models that you have developed, they are scalable, they are robust, and they are reliable. So the first topic, which we'll spend almost 2 hours on, is called cross-validation, hyperparameter selection, and metric evaluation. So this topic, which will last for 2 hours, will help you understand how to create robust models, and it will help you understand how you can evaluate your models to test whether these models are robust or not. We have two case studies in day two. Case study one that we'll discuss in day two is called sonic travel time prediction. So sonic velocities is very important for a lot of us who work on the subsurface characterization problem. And I'll show you how we can create robust methods for predicting sonic travel time, which will help you understand or which will help you quantify Young's modulus, bulk modulus, Poisson's ratio, and so on. So that will be a very interesting case study to look at. Towards the end of this day two, we'll talk about neural networks. I'll show you how you can apply deep learning. Again, deep learning is not the focus of this particular course. The focus is how to create robust models using machine learning and how to evaluate that your model is robust or not. One point that I want to mention is we'll end day two with a case study on working with sonic waveforms. All these sonic data that you capture, they are waveforms, and this waveform has a lot of data. I'll show you some unsupervised learning methods of how to work with these waveforms, which have a lot of information about the rock. Plenty of times, we use travel time. Travel time is the first instance when the waveform reaches a sensor. Instead of using travel time, if we use the entire waveform, we have more data, we have more information. So this particular case study will be a very interesting way in which you will appreciate the power of machine learning, which helps you process large data sets so that you can extract very good information, reliable information about your subsurface from large data sets.
Well, you have painted a very clear picture of what attendees can expect from your course, and that is one of the clearest explanations of AI and machine learning and deep learning that I've heard. So thank you for that clarity and the response there. Looking at something a little more specific, why is it important for geophysicists to learn Python?
Yeah, so Python as a language has become very popular. The reason I use Python, the reason I have heard a lot of my geophysicists, geoscientists, petrophysicists, colleagues using Python is the general purpose nature of this language. So, what I mean by general purpose nature is that Python as a language can be used for a lot of different applications. And that's what blew me. As in, when I started my computer programming, it was with Fortran. I started with Fortran, I used C++, then I moved into MATLAB. But once I reached to Python, which is, let's say, almost 7 to 8 years back, I was blown away by how versatile, how flexible this language is. It helps us solve a lot of different problems. It is very general purpose in nature. I'll give you one example. You can use Python to develop web apps. You can use Python to perform data analysis. You can use Python to do web scraping. What I mean by web scraping is to crawl the web and gather data. You can use Python to build games. You can use Python to perform data visualizations and very interesting data visualizations, which help us understand data even better. So it can be used in a lot of different ways, and that's why it is very important for geophysicists to learn Python. Once you learn a tool, once you learn a language which is so flexible, you can do a lot of creative stuff with it. Now, the second one is Python helps us automate. There are not a lot of languages that are designed for automation, and Python is one language which is designed for automation. And the beauty of automation is it helps us automate mundane, day-to-day, repetitive, boring work. And by automating those mundane type of work or repetitive tasks, what we have is free time to focus more on creative problems, focus more on doing interesting things. So that's why Python is an important language for the geophysicist. Now, let me tell you some more things why Python is useful and is important. Python is free. It is an open programming language. It is not expensive. It's almost free to use it. So why to waste money on things like MATLAB or things which require license, right? So instead of using those expensive software, what you can rather do is use Python. It is free, it is open, it helps us generate better visualization, it helps us perform exploratory data analysis. And the way you can use Python to manipulate data, that is very interesting. You can do a lot of creative data manipulation, extraction of things that you're interested in within the data for your own use. That is a pretty powerful use of Python. Now, Python has extensive support libraries. What I mean by that, I'll give you some example. If you want to perform scientific computation, then there is a package, there's a library called SciPy. If you want to perform data analytics, there is a package called Pandas. If you want to perform machine learning, there's a package called sklearn. If you want to perform deep learning, then you can import Google packages called TensorFlow. You can import it, you can use it. So it has extensive support libraries, which helps you do a lot of versatile type of tasks. It is flexible. It is these codes, this programming language is very easy to read, very easy to understand, very easy to learn. Python as a language is very portable, and my conclusion with Python, working with Python, is it helps me improve my productivity, and that is what is the most important thing. It is popular language, so a lot of job opportunities that are existing right now, you will see that one of the requirements would be a Python knowledge. So there are a lot of job opportunities that require Python. It has wide applicability. Scientists, engineers, mathematicians, statisticians, investment bankers, name it, almost everyone uses Python in some way or the other. Companies like Google, Spotify, Instagram, these are big companies, they use Python. If you're a startup, you will use Python because it's almost free. Federal agencies like NASA, they use Python. So this widespread use of Python makes it an important skill that each of us as scientists or geophysicists should have.
That is a powerful case for learning and understanding Python. You've definitely hinted at this in the last two answers, but kind of pulling it into one response here. What tools will the geoscientist add to their toolbox after participating in this 2-day course?
Okay, so machine learning is the focus of this particular course. Now, machine learning as a method can help geophysicists detect minute changes, variations, and patterns in high dimensional data sets. Data sets are increasing in size, they're increasing in complexity. And if you want to understand small changes or small variations, or if you want to detect a small pattern, then machine learning is a very powerful tool. And this course will focus on using some of these techniques for detecting these changes and patterns. If you want to identify similarity or dissimilarity among system or among different systems, among different processes, then machine learning becomes a pretty important tool. Machine learning is important for fast decision making. The reason it helps us make fast decisions is because it helps us process data that is coming to us at a very high speed from multiple sources and multiple channels. Machine learning helps us develop data-driven models that improve over time to represent the physical process and system and phenomena that we are interested in. If you want to perform precision engineering or precision characterization in the subsurface, for example, a specific diagnosis, then machine learning becomes a very handy tool. And as I just mentioned in a previous answer, for any type of automation of mundane, repetitive, low risk task, machine learning becomes a very important tool. Now, what tools will geoscientists add to their toolbox after participating in this particular course? So some very specific tools that they will get out of this course, if I kind of talk about them, they will learn how to assemble open source machine learning and data mining workflows in Python, and they will use that to solve complex data science problems. Participants will get better in performing exploratory data analysis on data sets that contain numerical, time series, and categorical data. And this data set is mostly from subsurface. So that's what the focus will be in this course, data that comes from subsurface. The participants will learn about supervised learning. They will learn about these tools called regressors. These regressors, they help us predict. And few regressors that they will get familiar with in this course are ElasticNet, Support Vector, Nearest Neighbor, Neural Networks, and Lasso. When we talk about classification, which is again one type of supervised learning, participants will get familiar. They will use decision tree, nearest neighbor, random forest, gradient boosting, support vector machine in this particular course. The reason they can learn so much in this course is because they're not developing anything from scratch. What I'm doing in this course is I'm providing them different modules. Some of these modules will contain classification type of problems. Some of these modules will contain regressors. So they are not supposed to develop anything in this course. What they are rather doing is they are focused on learning these things by applying it. So they will apply regressors, they will apply decision trees. Now, when it comes to unsupervised learning, I'll spend some time on tools such as k-means, dbScan, Gaussian mixture models, and self-organizing maps. The main focus of this course is to ensure that you develop robust machine learning methods. And to that end, participants will be able to apply training, testing, cross-validation, feature elimination, parameter selection, and anomaly detection on subsurface data. In terms of case studies, the focus will be rock typing, analyzing waveforms, predicting travel time, predicting saturation, and working on images. So these are some of the tools that the geoscientists and the geophysicists will learn from this 2-day course. It seems a lot, but actually it's not a lot, because what they're doing is they already have these tools provided to them, and they will apply these tools on data sets, and they will learn by applying. They're not learning by developing anything. They're learning by applying these tools on different data sets.
Yeah, that's what's so amazing about something like Python is because of all the resources and support available, you can really do a lot in a very short amount of time. So, as your course helps improve the geosciences to better harness the power and future of machine learning, kind of looking ahead, please finish this sentence. If machine learning in the geosciences reached its full potential, it could.
If it reached the full potential, what it could do is it will help us solve broader problems. Right now, machine learning can only solve narrow problems. Narrow problems, as in detecting if there is a cat in an image, narrow problem, as in trying to predict saturation. If it reaches its full potential, it can be applied to broad problems where geophysicist or some manager can ask a machine learning system, how can we solve problem X? And then these intelligent systems can spit out a solution saying that the right way of solving problem X is by adopting these steps. We are not there yet. And that's where we are heading. We have achieved significant success in computer vision, image analysis, natural language at this point of time. In the subsurface world, we are slightly behind. There's a long way to go. Today, we are applying machine learning on narrow problems, very specific problems. Machine learning can solve a small subset of problems at this point of time. But as we advance, if we give it 10 more years, pretty soon we'll start developing more complex problems. And the reason we can solve more complex problems is because machine learning systems, they get better and smarter with each time that they get exposed to the real world data. Most businesses, they have a lot of data available, but this data is in an unstructured format. Once we reach to the full potential, we'll be using all this unstructured data.
I want to kind of shift a little bit on these last two questions, kind of more for a general audience. You've been honored across numerous organizations and agencies, the U.S. Department of Energy and Society of Petroleum Engineers, to name a couple. Given your success, your honors teaching this course, what one piece of advice would you offer someone that would like to succeed in this field?
So, to succeed in this field, what you need to do is the first thing that you need to do is figure out a data set that you can work with. That's what I tell everyone. You cannot succeed in in this world if you don't have data. So the first thing that you need to do is figure out a data set, a large data set to work with. For example, recently Statoil, which is Equinor, a year back, they released large data set from one of their fields. So that data set is out there. That data set is it has, if I remember correctly, it has almost 100 GB or more worth of data. It has seismic, it has well logging, it has production data. So depending upon what you're interested in, get the data set first. Now, once you have the data set, then start defining your own problems. I'm in academia, and that's what my approach is. I first figure out a data set that I can work with, and then I define problems that have not yet been solved. And then I develop these methods. So, in my experience, almost 70% of times I was able to solve the problem that I defined. 30% of times you will not be able to solve these problems because of the lack of data or maybe the lack of information in the data that you just figured out, right? So figure out the data, then define a problem. And once you have the data and once you have defined the problem, then it's your time to take what you have learned in this course or to borrow advanced tools, advanced methods, and then apply it on your data set. The other thing that I would like to tell you is there are websites such as Kaggle. There are websites like GitHub. They have a lot of examples on using machine learning techniques. Most of those examples are focused on images. They are focused on time series data. So try to look at those codes which are written in Python. And once you understand those codes, try to apply those codes on your data problem that you just defined.
And lastly, kind of looking personally to you, if you could solve just one mystery as a geoscientist, what would you solve?
So I'm already trying to solve it. I have not solved it. So one thing that I'm after is, can we predict fracture propagation based on simple travel time data? So a lot of people have tried to solve it using physics-based methods. What I mean by physics-based method is using numerical simulation, using mechanical models of how a fracture propagates. I'm not using physics-based method. I'm not saying that physics-based method cannot solve this problem. Physics is required, but my focus is, can we use data-driven methods to predict how a fracture propagates in the subsurface? And one of the things that I'm doing for this particular work is I'm using a lot of numerical simulations. So these numerical simulations, they provide me data. And then I work on these data to develop data-driven models, which are slowly getting better at predicting fracture propagation. What we are doing recently is we are trying to take some of these data-driven models, which are already trained on simulated data from numerical simulators. We are taking it to the real world. There's a lot of data that has been acquired by Department of Energy. There's a lot of data that has been acquired by the Geothermal Office. These are all subsurface data. There is a lot of microseismic data, acoustic measurements, sonic measurements, seismic measurements. So we are taking these data-driven models and then applying it to real-world problems or the real-world data set that has already been captured by DOE and Geothermal Office. So that's the problem that I'm after. How can we predict fractures using data-driven methods? And at the end, this problem can only be solved by bringing physics and data together. It cannot be done just using data.
Is there anything that I should have asked you that I did not?
One thing that a lot of the participants would be interested to know is, how is this course getting offered in the near term? Now that we have this impact of coronavirus, a lot of the traditional classroom one-on-one type of courses cannot take place. So a lot of things are happening virtual. And I'm very excited about virtual courses. The reason I'm very excited about it is because I have started teaching virtual courses on formation evaluation to students from Texas A&M, and students seem to be more engaged. They seem to find more time to read, to understand what I'm teaching. So the benefit of virtual class is it increases convenience. Now you can access coursework from anywhere at any time. There is no barrier of location at this point of time. There's no barrier of time. So that provides a lot of flexibility. And when students or when participants of a course, they are given this convenience, they seem to learn better. This flexible schedule helps the participants be effective in time management. It helps them be more productive. For example, you can now take the virtual courses while you are doing some other task, which is not that demanding, right? So these are some of the benefits of virtual classes. It helps us retain knowledge because you are taking it in a environment which is very convenient to you. So it helps us retain more. It helps us focus more. I have seen an increase in student participation and student engagement on the pre-recorded lecture videos, and they are kind of open for more discussions because once you spend time understanding a particular concept through a virtual media, that's when you start asking questions. You cannot ask questions without understanding a particular topic. So students first look at these pre-recorded videos through virtual courses, and then that helps them frame questions, and then they ask questions. So students are now more engaged in this virtual environment. And one more thing, through this virtual environment, it helps the students and the participants sharpen their digital skills. And that's one of the focus of this course, how to make the participants more digitally skilled. And a virtual offering of the course also helps them improve their skills, because now they have to use this online world to access the material, to interact, to perform communication, and at this day and age, you can solve a lot of your problems through online digital media. And that will help you free up your time to focus on better, more productive things in the physical world. So this course, we'll be offering it as a virtual course because of this limitation of travel and limitations of meeting in a confined classroom environment. And I'm excited about this virtual offering because it will free up a lot of time for the participants to be more creative in the physical world, and it will help them be more focused in the digital world when they're taking part in this virtual course.
Well, that is a refreshing perspective and an insightful perspective to have about the value of the virtual courses, especially as so many things are shifting in that way right now. So I appreciate that perspective. I appreciate your thorough explanations of what students are going to get out, and not just students, all participants are going to get out of your course, and excited for all the lessons that people are going to learn from it. Thank you for your time today.
Thanks a lot, Andrew. You asked a lot of interesting questions, and thanks a lot for helping me and helping SEG spread this information about machine learning and about this course. Thanks a lot for this time.
Thank you for listening to SEG's flagship podcast. Please share this episode with a friend, colleague, or manager that would enjoy hearing this episode. Your recommendation is the single best action you can take on behalf of SEG's podcast. Go to our website at seg.org/podcast to find all our episodes and learn how you can listen to this podcast directly on your phone without downloading an app. Original music by Zach Bridges. This episode was hosted, edited, and produced by me, Andrew Geary. The SEG podcast team is Jennifer Crockett, Allie McGinnis, and Mick Sweeney. Thank you for listening. This is Seismic Sound Off, signaling off.